Hello everyone, welcome back to the third lecture in the lecture series of number theory. So in this lecture we are going to discuss about the greatest common divisor, that is GCD, its related properties and problems related to GCD. So first of all, let's try to understand what is a greatest common divisor. Well, the concept is very simple, but first let's look at the mathematical viewpoint. Given that if a and b are two integers and both of them can't be zero, at least one of them has to be non-zero, then if I say that the greatest common divisor of a and b, that's represented in this manner, GCD first bracket a comma b, if the greatest common divisor is d, then d must divide a and b, both of them. So that's number one requirement. And number two, if there is another integer that divides a and b, let's say c is another integer that divides a and b, then c must also divide the greatest common divisor. Okay, so if these two properties are satisfied, then we're going to say that d is the GCD of a and b. Let's take a quick example. Let's say I want to find out the GCD of 3 and 9. Okay, so we know that 3 and 9, the greatest common factor which is in 3 and 9 is 3 itself, right? So now we can observe one thing, the 3 divides 3 and 3 divides 9. So the first property is satisfied. Now in order to understand the second property in a more clear way, let's take another example. Let's say I am taking the GCD of 4 and 12. Okay, so the greatest common factor in 4 and 12, that's definitely 4. So the answer is 4. Now you can see the first property that's satisfied by default, because 4 divides 4, 4 divides 12. So first property, 4 divides 4 and 4 divides 12. So the first property is satisfied. Coming to the second property. Now if there exists some integer that divides a as well as b and it's not the GCD itself, for example in this case 2 divides 4 and 2 divides 12, right? So 2 divides 4, 2 divides 12, but definitely 2 is not the GCD. So then it is stating that it must imply that this new number 2, this must divide the GCD. So 2 divides 4, and that's definitely true. So both the properties are satisfied. That means the number that I've chosen over here, 4, that's the correct GCD of 4 and 12. Okay, so I hope both the properties are understandable with this example here. So now moving on to some properties of GCD. These properties will be very crucial for solving problems as well as doing other theorems. So the first very basic property is that if the GCD of a and b, let's say it's something called d, okay, let's say it's d, then this d can be expressed as the linear combination of some integers u and v. Okay, u and v are some integers, so I am taking the linear combination of u and v using specifically my input integers, which is a and b. Okay, not just any random linear combination, the linear combination using the input integers a and b. Okay, so let's take an example to understand this fairly. So let's say I go back to my same old example, GCD of 4 and 12, that's 4. So now this property is saying that there must exist some integer u and v such that 4 times u and 12 times v must be equal to the GCD value. Now the GCD value is how much? 4. So there must exist some integer u and v. So let's try to find that out manually. Okay, so here if I take or if I can divide the entire thing by a 4 first, so that it will help me in the manipulation. Okay, so I'm dividing the entire thing by a 4, so that would give me u plus 3 times v equals 1. Now it's easy to find out the u and v value because I have a 1 on the right side. So here I can say that if I take the u value to be 2 and the v value, or the u value to be minus 2 and the v value to be 1, then minus 2 plus 3, that would give me 1. So now if I plug this same value in this equation as well, okay, if I plug the same value here, so u is -2, so that would give me 4 times -2, and I'm taking the v value to be 1, so I will be having -8 plus 12, that would give me 4, which is the right hand side of my expression. Okay, so that means this property is giving me the guarantee for the existence of such u and v integers. In this particular case, the u value is -2 and the v value is 1. Okay, now there can be multiple answers. It's not that u and v, this value of u and this value of v is unique for this question. There might be more than one possible answer, but whatever be the case, the property is giving us a guarantee for the existence of u and v. Okay, now moving on to the next property, property number 2, it is saying that if we can take a k integer common, k has to be a positive integer. Okay, k has to be a positive integer. If we can take k common from both a and b, with or I can say if I can take a k common from both my input integers, then that k comes completely outside the GCD and the remaining values are there. Okay, so let's again take an example. Let's fall back to the same example that we have created here. Okay, so here I can express this as I'll just work with the LHS and I'll show that it's same as the RHS. So LHS, I have GCD of 4 and 12. So you can observe that I can take a let's say a 4 common from 1. If I take a 4 common from 4, then 1 is remaining. If I take a 4 common from 12, then a 3 is remaining. So I've expressed this thing in this format: k times a comma k times b. So my a value is 1 and my b value is 3, right? So the property is saying I can bring the k completely outside. So my k is how much? My k is 4. So if I bring the k value completely outside, I'll be remaining with GCD of 1 and 3. Now 1 and 3, they don't have any common factor. No common factor means basically 1 is always a common factor for any two integers. So the common factor of 1 and 3 is 1 itself. So the GCD of 1 and 3 is 1, and that would give me 4 as my answer, which is exactly the answer I should be expecting, right? So that means this property has been verified using an example. Okay, so remember that whenever there is some some positive constant, we can take common from both our integers, we can bring it outside the GCD. Okay, and lastly, coming to the third property, that we are going to say two integers are relatively prime. Okay, the word is important, relatively prime, if they don't have any factor common. That means one is always common, that's by default, so I'm not saying it that way. So if I say no factor common, that means one is common by default. Okay, so if they have no integer other than one common, then those two numbers are going to be relatively prime. For example, 1 and 3, they are relatively prime because the GCD is 1. Now we might ask the question that for two integers to be relatively prime, do the two integers have to be prime numbers themselves? Well, the answer is no, not required. Let's take an example. If I take GCD of 4 and 9, right? Neither is 4 a prime number nor is 9 a prime number. But do they have anything in common? Only one is the common integer, right? So their GCD is how much? 1. So that means I can say that 4 and 9 are relatively prime. Okay, now if I take two prime numbers, for example 2 and 3, both are prime numbers. So two prime numbers are always relatively prime, okay, because the only common factor is 1. So if I take two prime numbers, they are by default relatively prime. Okay, but if I take two integers which are non-prime but still they don't have any factor common other than 1, then we are going to call them, in any case we are going to call them relatively prime. Okay, so these are the three very basic properties. Using these three properties, we're going to do some problems. Before I start doing the problems, I just want to point out one more thing, that we can use property 1 and property 3 to make a new property. That means now if I say that A and B are relatively prime. So that means if A and B are relatively prime, that means that GCD is 1. And now from property 1, I know that GCD of two numbers can be expressed as first number times some integer u plus second number times some integer v, and the existence of u and v is guaranteed, right? So if I combine property number 1 and 3, if I have the information that A and B are relatively prime, which means that GCD of A and B is 1, now I can use property number 1 to say that there exists integers u and v such that AU plus BV is equals to the GCD, where the GCD is how much? The GCD is 1, right? So this is the conclusion that I can make if someone tells me that A and B are relatively prime. Now, why am I telling these things? Because now when we are going to face questions will have information of this sort, that A and B are relatively prime. Now we can't do anything with a statement like this unless we convert that statement into an equation. Okay, in maths equations are more important. We can work with equations rather than statements. So whenever this kind of a statement is given that two numbers are relatively prime, remember that this is the statement, or this is the mathematical equation that we are going to work with. Similarly, if someone tells us or gives us an information that GCD of two numbers is D, then how can I convert this information into an equation? The equation version would be that there exists integers u and v such that AU plus BV equals the GCD being D, right? So this is the equation format of this given information. So from now on, whenever GCD information is given, this is how we are going to convert that into an equation. When relatively prime information is given, this is how we are going to convert that into an equation. And lastly, one more thing, if some information of this sort is given, that A divides B, and I want this in an equation format, okay, that's again very simple. A divides B means that A, when multiplied with some integer, should give me B, right? So this is the equation format where I should always mention that K belongs to some integers, right? So if I say A divides B, then this is the equation format that will be required to solve problems. All right. So now let's take a look at a few questions. Let's say that it is given to me A divides B multiplied with C, and GCD of AB is 1, that means they are relatively prime. Then we need to show that A would divide C. Okay, so as I told you just now, we need to convert these informations into equations. Unless we have the equations, we cannot start working with them. So A divides B into C, that would mean that A times some integer is equals to B into C, and I should mention that K belongs to integers, right? Again, I'm going to convert this information into another equation, and I have already told you how the equation is to be written. So we'll say that there exists integers u and v such that AU plus BV is equals to 1. Okay, so I have got two equations. Using these two equations, I need to prove that A divides C. Okay, now let's think, what are we trying to prove? We're trying to prove that A divides C. Now what is the equation format of this? It means that A multiplied with some integer, let's say P, is equals C, so where P belongs to integers. So let's keep this in mind, that this is something that we are trying to show. We are trying to prove that A multiplied with some integer should give me C. Okay, that means A divides C. Okay, so I have these two equations, and from these two equations, this is where I want to reach. So now the entire question has been reduced to a simple algebra question. From two equations, create a third one. That's it. Okay, so let me tell you the process how we can do this. Achha, I need a c on the right side. Okay, as you can see, there is a c on the right side of the equation. So what I'm going to do, I'm going to multiply a c both sides to this equation. Okay, if I multiply a c both sides, I'm going to get acu plus bcv is equals c. Okay, now what I have is b times c, that is equals to a times k. So I'm going to substitute that over here and I'll get acu plus akv is equal c. Now my target is to show a times some integer. That means I need to take a completely common. So if I take a common here, I have cu plus kv is equals c. What I want is a times some integer is equal c. Okay, so have I already got that? Yes, I have got that, because u is an integer. See, there exists integers u, so u is an integer, v is an integer, right? C and k. Now what was k? K is an integer, so k is an integer. C was already provided in the question, so c is definitely an integer. So if I take the multiplication of integers and after multiplication if I take their addition, so the entire thing is still an integer. So what I can say is this is a times some integer. Okay, this thing I'm going to call as some integer p. So a times some integer is equal to c. So I need to mention that p belongs to z. Now I have reached my target equation which I wanted to reach. So this would mean that a divides c, and hence the theorem has been proved. Okay, so that was quite simple. Now let's move on to another question. Okay, so this is saying that if a and b are positive integers such that GCD of a and b is 1, that means again relatively prime. So just from this information I should be able to write the equation. What is the equation format? That there exist integers u and v such that au plus bv is equals to 1. So I've got converted one information into an equation. So as we have just one equation, it's difficult to proceed with a single equation. In the previous sum we had two equations, so it was easy to start doing the calculation with them. Since it's just a single equation, it's difficult to proceed. So let's try to create some more equations out of this. Okay, so let's say that let GCD of my required quantity, which is a plus b, a minus b, I need to prove that this is 1 or 2. So let me assume that, let's say this is d. So basically now I need to prove that d is either 1 or 2. Okay, that's my required proof. Now as I told you, the very first property of GCD, I'll just go back to that slide. Okay, so what was GCD? If GCD of a and b was d, then d would divide a and d would divide b, right? This was the very first basic definition of GCD. So if I just apply that over here, so if GCD of these two things is d, so that means d divides a plus b and d divides a minus b, right? So I have d divides a plus b and d divides a minus b. Okay, now let's come to a very simple concept of division. Okay, a very simple concept. If I say, let's take an example. If I say that 2 divides 4 and 2 divides 6. So using this two information, can I say that 2 divides the addition of these two numbers? Definitely yes. Can I say that 2 divides the subtraction of these two numbers? Definitely yes. It may become negative, no problem. 2 divides minus 2, no problem with that. So if what I'm trying to say here is that if d divides a and d divides b, then from this information I can say that d divides the addition of the two numbers and definitely d divides the subtraction of the two numbers. So if I add them and subtract them, the division is still happening. Okay, so no problem with that. It's a very simple concept of division. Okay, so if I apply that concept here, let's say d divides this entire thing, I call it a, and this entire thing I call it b. So d divides a and d divides b. That would mean d will divide the addition of both these things and the subtraction of both these things. Okay, so I can say that d divides addition of these two things would be 2a and d divides the subtraction of these two things would be 2b. Okay, so D divides 2A and D divides 2B. All right, now see that D is a common divisor. D is a common divisor of 2A and 2B. Okay, so I can write that D is a common divisor. D is a common divisor of 2A and 2B. Right? So that means that GCD of 2A and 2B, if I just take this GCD, okay, if I just take this GCD, then using the property of GCD, what I have is I can bring the 2 outside, right? If I bring the 2 outside, so I'll have 2 times GCD of A and B, okay? And GCD of A and B that was provided to me in the question, GCD of A and B was 1. So that means this is 2 times 1, so that's 2. So I have two informations here. One is that D is a common divisor of 2A and 2B, and the GCD of 2A and 2B is 2. Okay, so these are the two informations I have, right? Now again, let's go back to the very basic definition of GCD. Okay, this was the very basic definition of GCD. It was saying that if C is a common divisor, right? Here actually C divides A, C divides B means C is a common divisor of A and B. Okay, so here C is a common divisor of A and B. So if C is a common divisor of A and B, and if D was actually the GCD of A and B, then it meant that this common divisor divides the GCD, right? The common divisor C divides the actual GCD, right? So this was part of my definition. So I'm going to just use this property here. So what I have is D is a common divisor of 2A and 2B, and the actual GCD is how much? The actual GCD is 2. So what we have from the definition is that the common divisor, D is the common divisor, it divides the actual GCD, and the actual GCD is how much? That's 2. So this is coming directly from the definition of GCD. Okay, so I have D divides 2. Now what does that mean? So D is an integer which divides 2. So what are the numbers that can divide 2? The numbers that can divide 2 are either 1 or 2 itself, right? 1 divides 2 and 2 itself divides 2, and there is no other number which divides 2. Okay, no other, I mean positive numbers. Okay, so no other positive numbers which divides 2. So that means D is either 1 or 2, and this is what we were trying to prove. So we were trying to prove that the GCD is 1 or 2. We had started off with the fact by taking the GCD as D, and the value of D we have got is 1 or 2. So that means we have just reached our proof, right? So I hope this theorem is clear. Now let's move on to a very important series of questions. Okay, now you can see the number of stars I have put because this is a very important series of questions. Why am I saying series of questions? My actual question is to prove the third one. Okay, that means GCD, if GCD of A and B is 1, so that means if A and B are relatively prime, then A plus B and A square minus AB plus B square, these two terms have GCD either 1 or 3. I want to prove this. Okay, but first I have to prove this theorem, okay, or this given fact I have to prove. Using this fact, I will be able to prove the second fact. Using the second fact, I will be able to prove the third one, right? So in order to prove the third one, I need to first of all establish the first two. It's just like a chain reaction. If I'm able to do 1, using 1 I will be able to do 2, using 2 I will be able to prove number 3. Okay, so let's first focus on question 1, and then we will use that result to prove question 2. So 1 is saying that A, B, C are positive integers such that A and B are relatively prime because the GCD is 1. A and C are relatively prime because again the GCD is 1. Okay, so basically what we can say is that A is prime to B, A is prime to C, relatively prime to C, right? Then I need to prove that A will be relatively prime to the product of both the numbers. Okay, so A was prime to B, A was prime to C, then A will be prime to the product of the two numbers B and C, right? So let's start to prove this first one. All right. So it is given that, so I'm proving number one. It is given that GCD of AB is 1 and GCD of AC is 1. So very first thing, I'll convert these things into equations. Okay, so the equation would be that there exist integers u and v such that AU plus BV is equals 1. Again, I will convert this into an equation. Okay, so when I'm converting this into an equation, I'll not use the same integers u and v again, I'll use a different one. So I'll say that there exist integers m and n such that am plus cn is equals 1. Okay, so from these two equations, what I am trying to prove, now let's keep in mind what are we trying to prove. We are trying to prove that GCD of A and BC is 1. So that means we are trying to prove that A times some integer plus BC times some integer is equals 1. So this is where we are trying to reach. From these two equations, we are trying to reach to this equation. Okay, let's keep that in our minds. Okay, so I'll just keep this aside and focus on the given things right now. What I'm doing is, let me multiply this equation with, I can either multiply with the C into SCN or I can multiply with the AM on both sides. Now see, if I multiply with the AM, then I will be creating a A square term which is not required in my proof right now. So what I'll do, I'll multiply both sides of this equation with a C into N. Okay, so if I multiply both sides, I'll be getting ACNU plus BCNV is equals Cn, right? So I have multiplied both sides with a Cn. Now the purpose of doing that is that from this equation I have Cn equals 1 minus Am, and I can substitute this right over here. So if I do the substitution, I'll have ACNU plus BCNV equals 1 minus AM. Now I will try to take A common from these two terms. Okay, so if I take A common, I will have CNU plus M plus BCNV is equals 1. Now let's try to recollect what are we trying to prove. Okay, what are we trying to prove? We are trying to prove A times something, BC times something. Okay, so I have already got A times something. Okay, let's focus. A times something, BC times something. My something definitely has to be an integer. Okay, it's not just any random real number. The something has to be an integer. So B into C times something, something means an integer. So here the something is N into V. Okay, so B into C times N into V, okay, is equals 1. So we have got our required thing. So all I need to do right now is claim that this is an integer, this is an integer. Now that's quite obvious. C, N, U, those are integers, so their multiplication is an integer. M is an integer, so eventually the addition is an integer. And N and V are again integers, so the entire things are integers. So I can just call this K1 and I can just call this K2 and reframe the sentence as A times K1 plus BC times K2 is equals 1, where I've taken K1 and K2 from integers. So I have got my required thing. The moment I have got this equation, I can jump back to the previous line. The previous line would say that GCD of A and BC is 1. Okay, so I have proved my very first question. Okay, now let's roll back to the previous slide and see what is the second question demanding. The second question is saying that if A is prime to B, okay, if A is prime to B, I need to prove that A plus B and A into B are still prime. That means if I write this in terms of GCD, what question number 2 is actually telling me is that A is prime to B. That means if GCD of AB is 1, so that means if A and B are prime, I have to prove that GCD of the addition a plus b and the multiplication a into b, that is also prime. So this is what I have to prove. Okay, and while I try to prove this, I will require the help of the result of question number 1. So let's see how that can be done. So starting off with the given information that GCD of a and b is 1. Okay, so GCD of, so I'm doing the second question now. GCD of a and b is 1. So just one information is given to me. I'll convert this into the equation. So there exist integers u and v such that au plus bv is equals 1. Now I will do some manipulation to this equation. Let's say I am taking a dummy term. Okay, I am adding the term av and again subtracting the term av. Okay, so just a dummy term here, plus bv is equals 1. Okay, so what I can do now is I can take v common from these two things, or let me do one thing, I can take v common from these two things and a common from these two things, right? So if I take a common, I will have u minus v, and if I take the v common, I will have a plus b equals 1. So that means I can write it this way: a times u minus v plus a plus b times v is equals 1. Now this resembles like a times x plus b times y equals to 1. If this equation resembles something like this, then the conclusion is that GCD of a and b is 1, right? Because if GCD is 1, then there exist integers x and y such that ax plus by is equals to 1. So I can say that my a is this term a and my b is the term a plus b, and u minus v and v are the required integers x and y, right? So what I can say here is that GCD of a and a plus b is 1. Okay, I'm just for the my further benefit, I'll just reverse them and write it this way, that GCD of a plus b and a is 1. Okay, so I just rotated the terms, so they are basically the same. Okay, so this is one of the things I have got. Now again, I'll start off with the same equation and just do a different manipulation. That means a different dummy term I'll add and subtract. All right, so I'll just do that here. Again, starting from this equation, au plus bv equals 1. So now I'm adding a different dummy term. Let's say I add the term bu and minus bu, and the bv remains as it is. Okay, I again somehow want to create the a plus b term. Okay, how can I create the a plus b term? If I take common from here, if I take u common, and from here if I take this u common, so that will create the a plus b term. Okay, and from the remaining terms I'll take b and b common. Okay, so if I take a common, if I take u common, I have a plus b, and if I take b common, I have v minus u is equals 1. So again, this equation resembles this same old equation ax plus by equals to 1, where I can claim that my a is the a plus b and my b is the term b itself, right, where u and v minus u are some integers. Okay, so from here, just like the previous one, I can conclude that GCD of a plus b and b is 1. Now see, I'm going to use the result that I have got in question number 1. Now remember, what was the result I have got in question number 1? I'll go back to that slide. In question number 1, I had got that if the same term, okay, here the term was a, if the same term a has nothing common, or I would say is relatively prime to two different numbers b and c, then that same number is again relatively prime to the product of those two numbers. Okay, now observe carefully. Here a plus b is relatively prime to a, and a plus b is again relatively prime to b. So that means from the previous result, I can say that a plus b is prime to the product of both the two numbers, right? The product of the two numbers is ab. So that is also 1, and I have got this using the result obtained in question 1, right? So hence I have proved question number 2 using the result of question number 1, right? So now I have been able to prove question number 1, I have been able to prove question number 2. Now using the result of question number 2, I will be now starting to do the final question, the third one, which was by actual main objective. So it is given that GCD of AB is 1. Okay, so this is our given information. What are we trying to prove? We are trying to prove that GCD of A plus B, A square minus AB plus B square is either 1 or 3. So let me assume that this is D. So I'm trying to show that D is either 1 or 3. That's my final target. So I'm assuming that it is D. Now as per the GCD property, if GCD of two things is D, then D divides the first one, D divides the second one, right? So I can say that D divides A plus B and D divides A square minus AB plus B square. Now again, this is a common logic. Let's take an example to understand. If 2 divides 4, then isn't that obvious that 2 divides the square of 4? That's quite obvious. If 2 is dividing 4, that's dividing the square of that number as well. So what I'm trying to say is that if A divides B, then it's obvious that A divides the square of that number. Okay, because that same number is present twice now. Okay. So if I apply that over here, I can say that A divides A plus B whole square, and keeping this same, I'm not changing anything in this part. Now using a property that I've used before, if I have this is D, if I have D divides something and D divides another thing, then I can say that D divides the addition of these two things and the subtraction of these two things. So let me take the subtraction in this case, because I want to cancel out the A square and the B square. So I can say that D divides the subtraction of these two quantities, which is A plus B whole square and A square minus AB plus B square. So if I take the subtraction, if I break the whole square and take the subtraction, I'm getting a 2AB and a plus 2AB, so that's giving me a 3AB. The A square and B square are getting cancelled. Okay, so I have D divides 3AB. Now I'm creating a 2 columns and I'm going to study both the columns. So I already had the information that D divides A plus B. So I already had D divides A plus B. So I'm going to do basically 2 calculations simultaneously. That's why I'm creating 2 columns. And right now I have got D divides 3AB. Okay, these are the 2 informations that I have. Alright. Now there is one more information in the question which I haven't used yet, which is the GCD of A and B is 1. So I'm going to use the result that I have obtained in question number 2. Now see, what was the result obtained in question number 2? If GCD of AB was 1, if GCD of AB was 1, then the addition and the product, their GCD is also 1. So I'm using this result directly. Okay. So from question number 2, I have that GCD of the addition and the product of these two numbers is also 1. Okay. Alright. So if I use this information, pause. I can say that there exist integers u and v. Okay, so there exist integers u and v such that a plus b times u plus ab times v is equals 1, right? Now using this piece of information that d divides a plus b, that means if I want to convert this into an equation, I can say that d times some integer k should be equals to a plus b. So I should mention that where k has been taken from the integer set. Okay. So if I use this information right over here and plug in the value of a plus b, I can write it as d times k. So what I have is d times k times u plus ab times v is equals 1. Now why am I doing all these things? It will be clear to you very soon. Just observe one more small thing here. I have d times k into u AB times V is equals 1. What I can say from here is that GCD of D and AB is 1, because KU and V are integers. This is of the form AX plus BY equals to 1. The GCD of A and B is 1. Same format. So I can say GCD of D and AB is 1. Okay. So this is the information which I was requiring. The moment I have this, I will use this information right over here. Okay. Now I'll jump to that part. So I have got that D and AB have nothing in common other than 1. Okay. So D has nothing to do with the portion A into B, because D and AB are mutually prime. So if D and AB are mutually prime and still D is dividing 3 times AB, so that means what? D is actually dividing 3. Since D definitely not dividing the product AB, because their GCD is 1. So it's not possible for D to divide A and B. So what we have is D divides 3. So if a number divides 3, what can be that number? That number can be either a 1 or a 3. Because either 1 divides 3 or 3 divides 3 itself, and there is no other positive number which divides 3, right? So we have got D is 1 or 3. Now let's get back to our question. What was D? D was the thing that we were trying to prove as 1 or 3, right? D was the GCD of the original question. So we have ended up proving that the value of D is 1 or 3, and hence my theorem has been proved. Okay, so these are all the important theorems related to GCD. In the next video, we will be solving problems from Euclidean algorithm. You can find the entire playlist of the number theory series in the description below. Thank you for watching. See you in the next video.